First off, I'd like to welcome everyone to our session this morning here in Streaming Media West in beautiful Huntington Beach, California. My name is Ray Adensamer. I'm Director of Marketing with a new startup based in Canada called NETINT Technologies, and we are introducing an ASIC-based cloud encoding and transcoding architecture that I think has merits in delivering encoding at scale. But before we get going, quick show of hands. Who here in the audience is familiar with encoding and transcoding in a video streaming workflow and possibly using it in your organizations or businesses today? Very, very good. Very, very good. So you're probably familiar with some of the challenges and trends going on in the industry. We'll review some of those trends. The second thing we'll do is kind of do a quick review of some alternative architectures that are used for doing encoding and transcoding in a network. And then we'll spend a little bit of time talking about the benefits of our solution for addressing those challenges. Okay, so we'll start with a diagram, a high-level video streaming delivery architecture diagram. So obviously the objective is to take your video content, whether it's sports, celebrities, news, and get that to as many devices as you can. Now that source will often be captured at a very high resolution, 1080p or 4K, so it's going to look beautiful on your TVs here. But when it gets down to mobile devices, they have smaller screen resolutions, they got less bandwidth. So you're not going to send a 4K video stream to a smartphone device. It's a waste of money for your CDN spending, but also it's probably going to look bad. So somewhere in this workflow, you're going to need to do encoding and transcoding at scale. So this is going to take your input, typically captured using the H.264 codec, which gives you about 50 times compression, and then it breaks it down into what's called a bit rate ladder. And at the workshop yesterday, there was some good discussions about how to design those ladders and things like that. That ladder then gets forwarded into the content distribution network. That's where your ABR packaging is applied, maybe some of your DRM, and then it gets distributed to your display devices. So to summarize, why you need to do encoding and transcoding very well is for two reasons: to maximize the quality of experience for your end users, but most importantly, you want to lower the bitrate costs for your CDN distribution. So let's talk about CDN costs. So here we have a 1080p video that is being streamed for 1 month. And we're using the cost from Amazon CloudFront CDN. And so if you were to encode that using H.264, you can get a decent quality stream for about 8 megabits per second. So if you're going to stream 8 megabits per second continuously for a month to one person, that's going to cost you $51. But if you were to encode that same stream using H.265, which is a high efficiency video coding algorithm, that can reduce your bandwidth by about 50%. So by getting it down to 4 megabits, you reduce your cost in half. And you can see if once you've done your encoding, depending on how many viewers will view that encoding in the future, hundreds of thousands or millions, you can see it's a significant amount of money, a significant savings to distribute those videos using compressed codecs. And that's why services like Netflix and things like that spend so much money on their encoding, because this is how they can save so much money in their CDN distribution costs. So let's explore a little bit about what are the drivers for encoding and transcoding. So we'll start right at the top. So according to the Cisco Visual Networking Index, there's going to be 15x growth in consumer live video between 2016 and 2021. So what I'm here telling you today is that if the video, in terms of capacity and petabytes going through the network, is growing at 15x, the need for encoding capacity is going to be even higher. And it's going to be higher for three reasons. One is you're going to be using more compression codecs. So the H.265 that we introduced earlier, it gives you that bit rate cost savings, but the cost side is it's 10x the processing power in somewhere in your network to do that encoding, okay? So that's one of the reasons that encoding is going up. The second reason is high resolution videos. Most of the videos today are viewed in 1080p, sometimes in 720. There's a lot of early adoption of 4K. It's going to grow to 8K. It's going to grow to virtual reality. So higher resolution videos will also need more encoding processing power in your network. And finally is the trend about user-generated content. So here I wanted to show here on the right-hand side, you know, in the early days it was about sports, celebrities, and video demand world, the movies. So you would have maybe hundreds of titles that would then be encoded, but then you have the benefit of streaming that to tens of thousands or hundreds of thousands of people. So that the CDN savings associated with that allowed people to really look at encoding. Yes, it's a necessary evil. Yes, you can do it. But you know, the cost savings were significant. But the trend is now we're getting much more into user-generated content. So the number of unique streams, Facebook Live is a perfect example of this. Many unique streams going through the network, but you need to share that with your followers. But the number of followers is going down. Okay, so this is the trend going on in the industry from few encodings going to many distributions to many more original content pieces going to fewer things. So let's explore that relationship a little bit more. If I look at that line, I could also represent that line as the CDN savings from encoding. So again, sports, celebrities, movies, you got major CDN savings that are significantly higher than your encoding costs. So the encoding costs are a little bit higher for these because people want to spend that money to get that high quality encoding. But as this goes down, there's going to be a crossover point where if you have very few followers or viewers of that content, you're going to be losing money, right? So there is a need to reduce the cost for your encoding in the network. So the first benefit is obviously kind of obvious. If you can lower your encoding costs, you're going to improve your margins, right? And improve the profitability of your live streaming business. But the second benefit is maybe a little bit less obvious, is you're moving that crossover point further to the right. So what this means is that your encoding infrastructure can profitably support more live streams with fewer viewers. So with this trend to user-generated content, the industry needs to provide more scrutiny into how you're going to do your encoding at scale, how you're going to do that economically, and how you're going to grow that capacity, especially as we get into these trends for user-generated content. So how do you deliver transcoding in the network today? So most of the transcoding and encoding done today is using software on a CPU. The biggest benefit of doing it in software is it's flexible. You can use that CPU capacity for when you're not doing encoding or transcoding. You can use it for your billing, you can use it for your data analytics, things like that. But in reality, this is going to give you your lowest density and capacities. There are huge resource requirements and economic limitations to the scalability of this type of architecture. Typically in a one rack unit server, if you're doing 1080p H.265 encoding, you might get 5 streams per server. So how are you going to scale that? How are you going to scale that architecture for the thousands and thousands of encodings that need to happen to meet the demand for user-generated content? So very quickly, especially for live streaming, you realize that you're going to need some sort of hardware assist. So Intel has the quick sync video and some of their media software kits that go with that. That provides some level of improvement, but the quality sometimes starts to deteriorate. The more common one might be GPUs. Adding GPUs, again, it can improve your density and capacity, but GPUs are also known as a big power hog in your data centers as well. So there's a limit to the scalability around that as well. And I guess the most promising of these categories would be FPGAs, and there's a number of vendors here that are showing encoding and transcoding solutions on FPGAs. They use very specialized software called RTL that runs on those things. You're going to get your very high densities and capacities. The power efficiency starts to get a little bit better, but you do need to package that FPGA somewhere in the network, whether it's in the computer or in purpose-built hardware. So your flexibility is starting to go down a little bit. I think and finally, I wanted to make another point that all these options that I'm showing here, you can buy these options, or you can also rent them on a pay-per-use model. So here's some of the mappings of the Amazon EC2 instances to these various categories, including the F1 instance, which is an FPGA. So I think it's commonly understood in the industry that doing encoding and transcoding in an ASIC, application-specific integrated circuit, It's going to give you your best densities, your lowest cost, your best real-time performance, and your 80% less power. But the challenge that we've had in the industry in introducing these things is it's sometimes understood that this there's scalability problems because typically these products are built into purpose-built hardware. Also, it's less flexible. It's hard to change the software on these types of chips. And also sometimes the encoding quality is something you need to look at. So the ideal solution would be an ASIC to get you the performance, the density, and things like that, but in an architecture that addresses some of these concerns. And that's what I'm here to tell you about today. So we're here introducing the Code-Tensity T400 video transcoder. I'm holding it in my hand, right? We can do 8 sessions of H.265 video in this little device here. And I'll talk a little bit about this form factor in a few slides. But suffice it to say that this is designed to do scalable H.264 and H.265 video encoding and transcoding. It's got a killer capacity. We can do 4K transcodings in this up to 60 frames per second in one of these little modules. So that's the equivalent of 8 1080p streams that I already mentioned. So it delivers more capacity at a lower cost and significantly less power, 6 watts. This is less than a light bulb to run one of these things. And you put this in your network and you're gonna get the capacity and low power. And the other benefit of this is predictable low latency. And I didn't mention this with software encoding. When you load up those CPUs, when you're getting up to max utilization, it can do funny things to the latency. And we all know that latency is very, very important for live video streaming. With this, you get predictable low latency, as little as 1 frame delay through the box. So these are the benefits. So let's address some of the concerns that some of the audience might have with this. So first is how do I achieve that scalability and flexibility? So for that, what we did is we brought in some innovations from cloud storage architectures, and we're now applying it to the encoding and transcoding industry. So many of you are probably familiar that in the storage world, the mega trend is from hard disk drives. Here, I'll grab my pointer. Hard disk drives to solid state drives based on NAND flash memory. Now with that trend, there's also been a review of the protocol. So in the old days, it was SATA and SAS hard drives, way, way, way too slow for NAND memory. So what they've invented instead was something called NVMe, Non-Volatile Memory Express Protocol. Now when I say that, people are thinking, well, that's storage, that's storage. Well, yeah, it's got high throughput, very low latency. But most important, it's extendable. It's extendable for other applications, like encoding, right? So now let's talk about the form factor. So people are going to SSDs. The most common form factor to buy an SSD looks like this. It's called a U2, right? So there are devices from many, many vendors out there, a class of servers that's growing called an NVMe server. And we have some pictures of that on the right-hand side there. Where in the storage world, you would buy your SSD drive and you plug it into your NVMe thing, and that's how you build the capacity. And NVMe can be NVMe servers, it can be NVMe storage arrays, it can be even NVMe over fabric. So we can add very, very high density and coding capacity with this type of architecture. So here in the bottom, we were showing an NVMe server. It has 10 slots in the front. So 10 times 8 gives you that 80 sessions of 1080p H.265 sessions in a 1RU. So the flexibility comes by putting it into this package. You buy it from NVMe servers, so you're not locked in by proprietary hardware. There's many vendors providing that. And if you don't want to use these modules anymore, you can use that infrastructure capacity for your storage. So it's a very unique idea to address a common pushback on these types of architectures. The other thing I wanted to touch on was quality, right? So in the video on demand world, you have the benefit of time. So you can do your encodings, you can put it on slow presets, you can do double pass encoding. So in software, it's very easy to get very, very high quality encodings in a software on CPU type of encoding architecture. But we need to do this in real time. You need to encode these things, create that encoding ladder in real time. So here we've just done some internal benchmarking. and we compared so this is the PSNR quality score for our T400 solution compared to some comparables. So software encoding at faster preset. The NVIDIA GPU, very commonly used to scale your encoding capacity. We showed that we got a better quality scores than that, and then the Intel Quick Sync video at the bottom. So we've got a solution. It's got decent quality, and I know this is internal benchmarking, but it's being validated by some of our early customers as well. So the final thing I wanted to touch on was how do we integrate this into the network? So this is another elegant solution where many people here in the industry are using FFmpeg. Who's familiar with FFmpeg or uses it today, right? So you're familiar with FFmpeg. You know that it's an open source library of video processing and transcoding types of functions. So what you do is in that NVMe server, so it's a server, it's got Intel multi-core architecture and things like that. But because you're offloading the transcoding onto these devices, the utilization on those servers is very low. So you can add your FFmpeg. And what we do is we add a software patch that goes into the libav codec library of the FFmpeg. And through that patch, you can then recognize the resources that you have in that particular server. So if you're using FFmpeg, it's a very, very straightforward approach to adding this capacity to add significant capacity and performance to your architecture. So we also have some early customers. We announced the product on Tuesday, and we've had some early feedback from some of the customers we're working with in China. On the left-hand side is a CDN operator called China Net Center or Wangsu, and they validated that, hey, this makes a lot of sense. I can see how this can deliver the density performance at lower hardware costs. But what's more interesting here is YY.com. Now who here has heard of YY.com? Very good. I'm impressed. That's good. So YY.com, most people haven't heard of it in North America, but it is a significantly huge live video streaming social media site in China. It's actually listed on the NASDAQ with a market cap of 3.5 billion, 75 million annual users. And their business model is exactly what I was talking about earlier. They're working that right side of the edge. So they have many individuals streaming live video content, and they would have maybe tens or hundreds of followers following those video streams. Their infrastructure was getting crushed with the encoding requirements, and they were absolutely thrilled when they started talking with us. So we're continuing to do some early testing with them, but more importantly, I was pleased with they're saying, hey, the quality's pretty good. We're impressed. It's at least as good or better than what we're doing today. So in summary, I wanted to say, live video streaming, the volumes are growing at 15x. I think the encoding capacity problem is even bigger than that, right? It's going to grow because of user-generated content, increasing video resolutions, and also the increasing use of high compression codecs. We went through some of today's encoding architectures and some of those inefficiencies. You're not going to be able to scale to what the industry needs by putting in a rack server for every 5 sessions that you need. It's just not going to work. You need to look for alternative approaches. We think our approach has some merit, right, because it delivers high quality, scalability, and performance at a lower cost compared to alternative solutions. And we're the first to combine the innovations of ASICs with those storage cloud types of architectures. And we're already an early customer today, and I would love to get some customers going in North America as well. So my name is Ray Adenshammer with NETINT Technologies. Thank you very much for your attention. And at this point, are there any questions?
We have time for one question. Do we have a question for Ray? I am scanning the room. All right, we have one. Go.
Are you saying what kind of chip you are using in your module? Is that public information?
The chip we use in this is being developed in-house. So most of our engineers are ASIC engineers, and we call it the Codensity G4. We don't sell the chip on its own. Instead, we sell it in packaging like this for the transcoder market, and we're also doing SSD drives.
All right, round of applause for Ray from NETINT Technologies from the Great White North.